So this will be the concluding talk. It will be the only theory talk, yeah. So I will talk mostly about things that we hope to observe. Also about some things that we did observe, but mostly about what we are going to, hopefully, will observe. This work was done in collaboration with Tzvi, Paolo, and Elena. And or you will see that you will see many numerical results here. Everything was done very efficiently by Or. A student of mine should be somewhere here in the audience. Is yeah, over there. So I will talk about effects of the propagation of relativistic jets in GRBs and supernovae. So we all know that GRBs are associated with relativistic jets. We know that they are associated, the long GRBs are associated with collapsing stars, and therefore somehow the jet should go through the star. Also in the case of short GRBs, which are neutron star mergers, as Asaf mentioned, there is some ejecta which is thrown before and during the merger, and we expect the jets to propagate through this ejecta. And usually the star or the ejecta in the eyes of GRB people is considered as something which is an obstacle in the way. All we want is the jet to get out. We want to know that the jet can get out and do whatever it needs to do. In the case of the supernovae people, these collapsing stars also produce supernovae in the case of long GRBs. Well, there is some jet which is making some troubles, but at the end we want the supernova. We want the explosion of the bulk. As I will show here, actually there are quite interesting things which are related to the interaction between the jet and the ejecta. And this part was largely neglected. And I will show today that we can learn interesting things from this interaction. So this is the topic. So a few words, a few theoretical words about this interaction. So we have a jet. The jet is launched, I don't care how now, a relativistic jet with some opening angle. In the launching mechanism, in the launching site, we know the launching site knows how to accelerate it and how to collimate it to a conical shape. And I start from there. Now it starts interacting with the medium around it. What happens? The jet needs to go through this material, so it is producing a shock at the front. There is a head. This is an enlargement of the head. We have a force shock going into the outflow, into the ejecta, into the surrounding medium. Reverse shock going into the jet. And here we have a very, very high pressure material. Now this head, even if the jet is ultra-relativistic, this jet, for typical parameters, is Newtonian or mildly relativistic at most. And the material from this head spills to the sideways. High pressure here, low pressure here. So all the time, the jet is drilling through the star, and the material is spills to the side, and it's building up what is called the cocoon. This is a very high pressure, which is surrounding the jet, and actually, by applying, because the jet is cold, it's applying pressure on the jet and collimates it. So the jet is starting with some angle. It's collimated to some opening angle. It's conical. Above this location, it's actually becoming cylindrical. Actually, very simple considerations can show you that if it was remaining conical, it couldn't break out of a star. You couldn't, if you would like to take a relativistic jet and propagate through the star conically, the requirements, energetic requirements are even beyond what GRBs can make. So actually, in a sense, the jet is collimating itself with the help of the external medium, and this enables the jet very efficiently to penetrate through the star, getting out, and give us the GRBs that we see. Now, in the process, all the energy which is dissipated in the jet is going to this cocoon. So at the end of the day, by the time that the jet went all the way out of the star, all the energy launched into this jet is actually remaining in the cocoon. Later, it's breaking out of the star, or of the ejecta in the case of a short GRB, and giving us the GRB itself, giving us the gamma rays that you observe and the afterglow and everything. But in the process, all the energy, and this is a considerable amount of energy, is located in the cocoon. So this is a cartoon. This is a slightly more elaborated cartoon obtained on a computer. So you can see here again the same features. Slightly more messy, but the same features. You see the collimation shock, so the jet here is conical, it's becoming cylindrical. Here is the shock that collimates it. This part is a cocoon. The cocoon is actually separated into two regions. You can see it here. You have the material which is spilled out from the jet, which is very hot and light. You have the material which is spilled out from the star, and also the material which is shocked by the shock which is propagating in this direction, because the pressure here is high and the pressure here is low. And this part is very heavy. Here you can see it in 3 dimensions, and again, the pinkish curtain is the surface of the cocoon, and the red part is a jet, which is largely stable up to the head. Now, if we would like to see it, how it propagates in time, so this is a star, and here in the center you see the jet. It's very narrow at first, and it's propagating, building up the cocoon, remaining relatively narrow. Actually, the opening angle of the cocoon is comparable to the opening angle of the jet at the time of launching. And you see that there is a point where it's breaking out. Now, when it's breaking out, the jet is continuous, and actually it's interesting to see what is the interaction between the cocoon and the jet, but let's put it aside. What you will see, that all this hot material, all this energy which is contained here in the cocoon is actually now free to spill out. And this material has a range of Lorentz factor, has a range of velocities. It's actually, if we see how much energy we have as a function of the Lorentz factor, it's almost uniform in log space between velocity of about 0.1 c and a Lorentz factor of, say, 5 or something like this. So this will produce a wide angle emission with a large range of frequencies. Just to see the energies here, so in the GRB we have about 10 to the 51 ergs, this is in the jet. Comparable amount of energy we have in the cocoon, and supernovae usually, which is, there is another explosion here, which is not simulated. There is some spherical part to the explosion, which is actually putting 10 to the 52 ergs. But as I said before, there are hundreds, probably thousands, of papers about the GRBs and about the supernovae, and maybe half a dozen, maybe a dozen papers about this cocoon, which contains the same amount of energy, a lot of information, much harder to detect. Yet, it is becoming possible now with time domain astronomy, which is propagating very, very fast. So the emissions that we expect to see is in very wide angle, wide observing angle. We expect to see an optical, UV optical actually, not only optical. In smaller angles, but still much larger than the jet itself. So if this is about 10 degrees, so this is about something about 30 degrees, we expect to see also X-ray, UV, and optical light. How does it look like? So this is a result. If you take a numerical simulation and you calculate what is the emission, here I concentrated in the near UV and the G-band. You can see this is emission for different viewing angles. You can see that up to an angle of about 45 degrees, 0.8 radian. You get a bright signal, time scale of several hours, almost a day. It's as bright as a bright type 2p supernovae, or a faint type 1a, very faint one. Minus 17, minus 18, something like this. And it can be seen for each GRB that we observe, which is observed only to within 10 degrees, we have about, 50 that produce this signal. So these signals are going to be observed in the near future. Several years with large-scale surveys, we are going to detect this signal. We can learn a lot about the progenitor, about the jet itself, about the true rate, because we don't have the beaming. And this is very interesting, but this is, in a sense, incremental. We know that GRBs have jets. We know that there are stars. We know that there is a propagation. This signal must be there. So we can learn more properties about the GRB. But can we use this cocoon to learn about things that we don't know that if they exist or not? This is much more interesting.
If they're so much more common than GRBs and they're as bright as type 2 supernovae, why haven't they been seen?
For an hour. And the GRBs themselves, even after compensating, are much, much, much less frequent than type 2 supernovae. So you have something which is much less frequent, let's say 1% of the rate of the supernovae, slightly more, comparable in How many type 2P supernovae were observed within an hour after explosion?
You can see them just this.
Yeah, but I say, how many type 2Ps were observed? Take the type 2Ps, the number of them that were observed an hour after the
How long after? It's less than an hour.
Average distance. Type 2 Ps, you see a lot of them. 100 megaparsec you can see easily. The nearest GRB, this sort you're talking about, is not 100 megaparsec.
No, it's much more than that because they're much less frequent.
It's there, but
It's there, it's very difficult. Even with ZTF, you expect to get something like 1 a year.
minus 18 now.
Yeah, this is because GRBs are much less common than type 2Ps. This is what we're getting. Yeah, per unit volume, of course. So there are very strong evidence, I will not get into it, that not all jets in GRBs are actually successful. Some of the jets die before they break out. So there will not be a GRB because there is no jet. But still, something happens. So let's see, for example, what happens if we take a jet, let it propagate, and then here, we shut off the jet. So there is a star here, believe me. This is gamma beta, so you don't see the star. And here we are about, the star is that's the size of the slide, so this is about a quarter of the way out of the star, and here we kill the jet. What will happen? So there is a cocoon, and you see this, the cocoon continue to expand. It's actually not becoming spherical very, very quickly. And it continued to expand. Now you see the edge of the star. It starts accelerating because of the gradient in the density of the star. It's relatively narrow collimated. Also at the time of the breakout, which is here, the size of the cocoon here is, I don't know, maybe 20 degrees, something like this, maybe 30 degrees. And it depends. If the jet would be, if I would stop the jet halfway, it will be even narrower. And many of them supposed to stop here. So this event must occur. Actually, they're probably more frequent than regular GRBs. And after the breakout, the cocoon is spreading quickly. It's also accelerating. So if you look at the velocity here, this is 0.1 c, this is about 0.3 c. So we have here a lot of material moving at about 0.1 to 0.2 c. This is velocities that you do not expect to see a lot of material moving in a regular supernovae. And it's relatively spherical. And later, when the supernova is coming out, all this material is supposed to be in front of the supernova. So first it's supposed to radiate, and then it's supposed to stand there and wait and absorb. So if we ask, can we see this? Now this is more interesting than GRBs because we don't know about these events. We never saw events like this. So can we see it? So the answer is yes, and you can see it in two ways. One way is, again, looking for the direct signal. It will be short, hours, it will be blue, and it will be comparable to what we have seen before, slightly fainter. We don't know exactly yet because we didn't calculate it yet, but we'll know soon. But there's also another way to see it. As I said, this stuff will absorb the light coming from the supernovae later. How should it be observed? So what will be the observable signal? What will be the observable signal from this absorption? So, yeah. So one of the things that can be done when we have an early spectra is by looking at the lines and see the velocity of the line, it's possible to estimate how much material it's moving at which velocity. And then at the end, one thing that can be constructed is this distribution of energy as a function of velocity. So basically telling you how much energy is contained by material moving at a given velocity. If we take a star, explode it spherically, this is mostly what you expect to get. So this is the bulk of the material moving here. Typical velocities is 3,000 kilometers per second for regular supernovae, the fastest broadline supernovae, 10,000 kilometers per second, something like that. And then here it's supposed to fall up very, very, very quickly. And actually, if it's a spherical explosion, you can play with this, playing with the structure of the star. You can change somehow how fast it's going down and doing some weird things, but it will never go up. It's I don't know, completely impossible, but we couldn't think about any way that this distribution should start going up somewhere here, if it's a spherical explosion. Now, what will the cocoon do? If I just look at the cocoon, I take a larger amount of energy, which is the energy in this jet, and I put it directly. The reason that I don't have a lot of material moving a lot of energy in fast-moving material, when in a spherical explosion, I deposit the energy in the center, and the energy is going directly to the bulk, and the bulk giving a small part of its energy to the material outside. The jet is going directly to the part which is outside, taking a small fraction of the material and putting a lot of energy here. So the jet is going beyond this, and it can put a lot of energy in fast-moving material. So this, if the bulk was about here, so I can take about 10 to the 51 ergs and now put it in about a fraction of a solar mass. So this will move in a velocity of about 0.1, 0.2 c. Combining the two together, we expect to see distribution of how much energy is a function of velocity that looks like that. Now this was a prediction. So then we ask, okay, but we do have observation of some supernovae early enough to see for that. Does it exist? As it turned out, it does. So what you see here, this is the work done with Paolo Massali and Elena Pian. What you see here is published distributions. So all these supernovae, the first one observed 20 years ago, published 17 years ago. We didn't do anything. We just took what was published in all these papers, all the papers discussing this, and plotted it. In these papers, it's usually described as a density distribution, but density distribution with a velocity can easily be converted to energy distribution. And when you plot it as an energy distribution, this is how it looks like. So in the black line, you see the expectation from a spherical explosion. You see that in all these supernovae, and there is various types of supernovae here. In the next slide, I will show you which. You see something here is strange. Most noticeable is this first one, 97 EF. We have a well-separated component with a lot of energy at very high velocities, about 0.2 c. In others, we have also a lot of energy in very fast velocities, much more than expected. In this one, O3BG, we have this weird bump. So I would say that 97 EF, there is a very strong signature of a jet in a supernovae. No GRB in this supernovae. And also in O2AP, a supernovae observed 8 megaparsecs away, no relativistic motion whatsoever, the fastest velocity observed, 0.3 c. Very strong evidence for a jet. In others, the evidence for a jet is, for example, is BG. There is an evidence for a jet, but maybe it can be produced also by other means, I don't know.
What's the scale, the velocity scale?
So it's all normalized, so they will fall on this. But typically, the break here is about 0.1 c. It's between 20 and 30,000 kilometers per second in all of them. Okay?
And this is a velocity that's deduced
From the lines.
It's not really seen in any line, is it?
You see the width of the lines.
There are lines at that width?
Well, the width of the line is almost the entire spectrum, yes. So the way it is done, it was done by Paolo. The way it is done is by running a Monte Carlo simulation that mimics the radiation through this. The input is a profile of the ejecta, and the output is the line that is a spectrum that's observed. And
photospheric.
Yeah. Well, it's not only photospheric, but yes, basically. Yeah.
Can you show, do you have a spectrum of the actual spectrum? With the
In the paper, not in the papers that were published, not here.
But can you clarify how exactly you determine the energy per velocity?
Yes, so, well, not exactly, but I can tell you what Paolo is doing. The input, Paolo has a code where the input is a distribution of a material, so the distribution of velocity and composition, and the output is a spectrum. And then he plays with this and asks what is the distribution that I put in order to get what I get, what I see. The solution is not unique in a sense, but you do need, in order to have line blending at the level observed, you do need material moving fast enough and enough material doing that. Okay?
And it's based on 1 or 2 spectra per, early spectra per event?
It's basically when you move with time, you probe different different location within the outflow.
But here you related to just one or two spectra? Or
No, the entire spectra is Paolo did the entire fit to all the entire sequence, but the high energy stuff can observed only in 2 or 3 spectra and only within 2 or 3 days. No, sorry, up to about a week. After a week, you don't have a spectrum within the first week, nothing. You cannot do it.
But just to sharpen, in none of these supernovae, nobody has actually seen material moving at point 1c.
No, this is not true.
No.
No.
The absorption lines extends. The bluing of the absorption line extends.
Not only. In the radio, you see material moving at this velocity. In the radio, you do see material. Nobody seen that.
Spectra, if I understand correctly, from the spectrum that he sees, where there's even the furthest wings have much slower velocities, he deduces that inside there must be material moving at these high velocities. Am I right?
No.
No, you see absorption lines. The fact that calcium 2 and oxygen 1 on the red side are blended means that there must be material moving at 0.1c in the optical spectrum at early times. Yes.
The fact that they're blended?
Yeah.
That they're broadened, you mean?
They brought it to the point where they actually.
You have 2 lines separated by 1,000 angstrom, and then they are blended together into a single line.
Okay.
So it means that.
By the way, specifically in the case of 2008 AP, there is a spectropolarimetry. When you look only at the velocities, and the polarized light is redshifted compared to the unpolarized light, suggesting about 0.1 solar masses moving at the velocity of about 0.1 c. So this is completely different, and this is a paper that was published just after them. So suggesting very consistent with what we see here with a very different. Yeah.
But the main thing is not the 0.1c, which is 30,000 or 20,000 kilometers.
The main thing is 0.1 c and 0.1 solar mass in 0.1 c. This is the main thing.
So the main thing is the mass estimate.
Of course, is the mass and the velocity. You need both.
Yeah,
Each one of them.
mass, well, you need to think first the mass and also the extension to several times larger velocities, because this is just the break. So how reliable is the mass, and how reliable is the inference that you showed on the plot, that it extends to 5 or 6 times larger velocities?
No, it's not.
The break was at 0.1.
The break is about 0.1, and we see to about 0.2 or 0.3. That's it. After that,
You can show the previous slide. It extends
from about 2 to about 4. So about maybe 1.5 and 4. So we have about a factor of 2 or 3 above 0.1. So we have to go with 0.2 or 0.3c.
So I assume no one saw 0.3c in lines there.
I'm not, well,
So this is sort of an inference, an indirect inference.
no, I don't care about the 0.3c. I care about the 0.1c. I care about where most of the energy is, which is above the break. So about between 0.1 and 0.2, this is what I care about. How reliable it is, you should ask Paolo. Really, so,
He's not here.
which is not here, yeah? Yeah. So, yeah, no, really, he claims, when we asked him, he claims that there is no way that he can explain the spectrum without having this amount of mass moving at velocity faster than 0.1 c. And this is all I care about. All I care about. I don't care about, and I asked him also another thing, can I have all the material moving at between 30 and 35,000 kilometers per second? Because this is something I can do with a spherical explosion and some weird things with a structure of the star, and the answer, definitely not. So we didn't redo what Paolo did. But, so what do we get from that? We have 6 supernovae that we observed. This is everything that we observed, that we looked for, because we need data which is good enough, and it was already analyzed in the past. All of them show some evidence for energy, for high velocity material, which is indicating possibly on the jet activity. And you can see that many of them are 1C broad line, which is okay. They are associated with GRBs. It's not very surprising. Some of them, as I said, 2002 AP definitely didn't have a GRB. But okay, we expect to have some choked GRBs. Maybe here, okay, choked GRB, nice. But the most surprising part is that we have also a 2B and a 1B. Now in the 2B I said it's marginal. In the 1B, it's much more, in this specific case, it's much more, the signature is stronger. And if this interpretation is correct, then it seems that a large fraction, possibly all, I don't know, but a large fraction of all hydrogen-poor supernovae contain relativistic or at least mildly relativistic jets. Now, if this is true, then I think we need to rethink about what is explosion mechanism. It's not trivial. Well, with neutrinos-driven explosion, we cannot get this. We cannot get jets, relativistic jets, with neutrino-driven explosions like what is a common explosion mechanism or the favored explosion mechanism for supernovae.
Why can't you have both jets and neutrinos?
What is production? Oh, you can have both. Maybe. Well, the neutrino is doing one thing and the jet is coming from another thing. Then, but then you need to explain how you do that. And second, it indicates that we have a compact object rotating very fast. Okay? Which probably has something to do also with the explosion. So this, I think, is a very exciting result. And well, we'll see more. We'll know more when we have more observations like this. Next, a few words about short GRBs. So as I said, we expect the jet to propagate through material which was ejected during the merger of neutron stars. And Asaf has shown some of the signatures that we expect. What about the interaction between the jet itself and this material? So what you see here is a simulation of a wind, which is a reasonable wind expected, and a jet from a short GRB. And what you see here is a cocoon, which is breaking out. So this is a jet, this will produce a GRB, and you see that this cocoon here is again moving at wide angles. It contains a lot of energy. This material is now also radioactive. So we'll have two modes of emission. One emission will come from the cooling emissions, the photon escaping. So we have, when the jet propagates and everything here is shocked, a lot of photons and internal heat is produced, and this heat and photons will diffuse to the observer. This is one mode, and the other is the radioactive decay will also power the emission.
So, okay, I don't understand this. You expect to get a heavy wind before the jet starts propagating?
Yes, so the most, say, convenient way to do it is to have a delay between the merger and the collapse. So you expect, in many scenarios, you expect to have a hypermassive neutron star, which is the first thing which is formed. It's mostly supported by differential rotation and by neutrino pressure, but this is supposed to last to a fraction of a second. And then after, say, 0.1 second, in this simulation, we waited about something like 0.1 second. It will collapse to a black hole, and then the jet will be launched. Before that, we have material coming from the dynamic ejecta, and we have also a lot of wind coming from the hypermassive neutron star and from the disk. So we have about 0.1 second where a lot of material has time to expand. And then it is launched. Even if you don't have that, even if you have merger and then it is launched, then you still have the dynamic ejecta that was ejected earlier, which some of it will cover also high latitude regions. So it's not like you have everything emitted in the plane. Also during the merger itself, during the contact between the two neutron stars, there is a claim that a lot of material is ejected. So you'll have material ejected, but this will not have enough time to expand.
That's what I'm trying to say is that, of course, no one has found a signature for any ejecta yet, but you would want to have some mass in this ejecta. And in this game, 0.1 solar mass is a very big number.
0.01.
Yes, it's a very big number.
0.01? This is a number that most people coming up with.
I've just said this is not yet a thing. If you ask, if you look at the few fits people do, to the early optical observations. Now, look, this all as far as, okay, if you look at Shibata's model, 0.1 is extremely rare. You need some very special.
You have something with 10 to the minus 3 and 10 to the minus 1. Here I have 10 to the minus 2, for example. 10 to the minus 3, this is the lowest amount that Shibata is finding. And 10 to the minus 3 will give you a similar signal, actually. It's not well, it will be slightly lower, but not much lower. Observationally, I do not believe any of the claims that we have any idea. So all the macronova signals, I don't believe that they are really macronova. So I don't think we have any observational signature of ejecta. Here, honestly, we don't know. It's possible that there is that the amount of ejecta is low, and that there is no delay, and there will be no signal. It is possible that what we took here is conservative. So we have a full range. This is a plausible possibility, certainly not a guaranteed outcome. Okay, so yeah, theoretically we do not understand mergers well enough to know exactly what will happen here. But this is it's a reasonable outcome. One thing, there is some indication looking at the duration distribution of short GRBs, suggesting that there is an imprint that it takes some time for the jet to break out of something. And this time is about 0.3 seconds. Now, if you take this outflow and you calculate what is the emission that you expect to get, so these are busy slides, but this will be the last slides of my talk. What you see here on the top, we really don't know what is the optical depth, what is the opacity of this material, of the material ejected in the neutron star merger. Two typical values taken are a kappa of 10 centimeters square per gram or 1 centimeter square per gram. So this is the left and right. And here you see what different observer will see in the G band. Here you see what an observer of 0.5 radian will see in the different bands for these two possibilities. And you see that there are two components here. Here it's seen more clearly. One component is coming from the radiation which is escaping. This is a cooling emission. The second is dominated by the radioactive decay. You can see that the first one is coming after about 10 to the 3 second, something like that, almost a few hours, maybe an hour. And the second one is coming after more than 10 to the 4 second, several hours. And you can see that the opacity is changing the ratio between them. So if we have high opacity, the first peak is brighter and slightly later. If we have low opacity, the second peak is becoming brighter and even later. So in this case, even if we don't know what is the opacity, we're in a kind of a win-win situation. The opacity can be even higher than 10. So the opacity is the main uncertainty here. Well, not the main. It's a major uncertainty in addition to all the uncertainties that we have in how much material and what is the delay and whether neutron stars are associated with GRBs or not, really. So if you take everything up to here, then opacity is what is keeping you. But one of the concerns, the opacity will be high, and then all the other signals are very faint. Actually here, high opacity helps us, because the first peak here is coming from when the material is very, very hot. So what we see here is kind of the Rayleigh-Jeans part of the spectrum. Higher opacity will actually help us. It will bring the temperature closer to the optical and UV bands and make it easier to detect. And the brightness is very bright compared to other signals. We get to minus 15, which at the distance of 200 megaparsec is making it observable. Now, with different parameters, I can take this figure and put it 1 or 2 magnitudes down, but also 1 or 2 magnitudes up. So this signal may exist, and maybe it's existing, maybe it's not, maybe it's too faint, but there is a reasonable chance that it is detectable. And if it is, then, well, if you can use it to identify the locations and the electromagnetic counterpart of gravitational waves, it's huge. So this is a summary. For long GRBs, the cocoon emission will probably be detected, will teach us interesting things. For choke GRBs, we think that we have good prediction, good evidence that there are many jets, but the data is out there. A lot of data will come later, and Ellie, you are welcome to analyze it and see how significant it is. No, you have the data. The data is this. For the supernova we have, the data is this. You can take the data, you can do whatever you want.
You just have to build a satellite.
Oh, this is for, okay. When you will have time, in a few years. And for short GRBs, the possibility is that there is a detectable signal here that will enable us to pinpoint the location, the electromagnetic counterpart of gravitational waves. And, well, it's a good point to conclude. Thank you very much.
I'll take the first question, actually. So
A very questionable chair.
yeah, you had the plot for all the bands and UV. Will there be an X-ray signal?
No.
Why not? It keeps on going up, no?
No. You go in the Rayleigh genes and you get to the peak and then it goes down very quickly. So the it's unluckily, most of the signal is not only true for the short GRBs. If we would be sensitive at about 0.1 keV, it would be great. Even less than 0.1. So the temperature is typically starting. It's starting so it's starting at 10 to the 45, 10 to the 46 ergs per second. It's very bright in this case. But temperature of about 0.1 keV, slightly less than that. So you're just at the point where you cannot observe.
0.1 is X-ray enough for me. Because, no, the reason I ask this is because
It's even below. It's even slightly below that, and because of the exponential cutoff.
on Sunday, Neil Brandt gave a talk, and he showed that in the Chandra Deep Field South, which was observed altogether over 3 months or so.
Yeah, I saw it. Yeah.
At some point, they had something that looked just like this. Lasted an hour.
Mm-hmm.
It's a few tenths of a keV.
Okay, so this for short GRBs.
And they calculated that the rate is like the rate of GRB.
Yeah. So okay.
But
So
there's a limit on the distance. This cannot be very.
no. But he's talking about long GRBs. For short GRBs, no chance. Short GRBs, it will not be.
I'm not saying it's a GRB, right?
No.
He just said that the rate is like the rate of, the rate of short and long GRBs is the same.
What I'm saying is it's a cocoon from a short GRB, there is no chance. A cocoon for the characteristic for the cocoon, it will be too faint. It cannot be that what Neil Grant saw.
What he saw was very faint.
No. Well, it's really very faint. Not very faint like what he saw. He saw 10 to the 47 ergs per second, 10 to the 46 ergs per second.
That was what he.
This is what he called faint. It's faint compared to GRBs.
I don't think he knows what the distance is.
Yeah, but there's a lower limit because
No. There is a host galaxy, the redshift is between 0.3 and 2.3. So even putting it at 0.3, it was about 10 to the 47. It was faint in GRB terms. So if you look at GRB afterglows, they are much brighter than that.
But it was still much brighter.
It was brighter, for example, than the 2008D. So this is the only X-ray observed directly from a onset of a supernova. It was brighter than that by about a factor of 10. So in principle, you can get it in long GRBs if you push the limit. Because as I said, this is 0.1 keV for typical parameters. Maybe you can get to about, and the spectrum was rather hard. If the spectrum was very soft, then okay, but the spectrum was rather hard. Maybe you can do it, I'm not sure. There is a good possibility this material will also produce an afterglow. It might be the afterglow from the cocoon. But for this, we need material moving relatively fast, Lorentz factor of 20, 30 at least. At least in our simulations, we do not. In 2D, actually, if the word was 2D word, then in 2D we get these velocities. In 2D simulations, we get material that will do it greatly, but in 3D not. So it's possible, but
Can you go back to that table with the supernova parameters? Yeah. Okay, I'm not an expert in this modeling, but I worry a bit. Is there any evidence that 2008D, for example, is 6 times 10 to the 51 ergs?
evidence from the modeling.
Last Avisha, that seems to be very high for what appears to be an ordinary 1B supernova.
I'm not sure. I think that Doron, I'm not sure if he is here, but he compiled all the energies of type 2s, 1Bs and 1Cs, and he's shown that 1Bs and 1Cs are more energetic.
Yeah, but it's true what she said. This is a bit high for 1BCs. I think other people get different values for the total energy. Depends a lot exactly on how much mass you put at high velocities.
Yeah, well, I'm just...
No, actually here's no, but this is not dominated by high energy. The energy here is not dominated by high energy.
Okay.
The fact that, well, if it's, no, by high velocity, so the energy here is not dominated by high velocity material.
A simple thing. We look at all the galactic supernova remnants. To my knowledge, there is, okay, I could be wrong, but to my knowledge, there is no evidence for core collapse supernova to exceed 10 to the 51 Earths in a galaxy. Just, it's total calorimetry, which is very easy to do. Okay, there's some radiative losses, we can put that in. That's the thing I always carry in my head, but maybe I'm misremembering something. So I worry a bit about all that modeling, that dE by d log beta, frankly.
Actually, they are not related directly. So this result is coming from the normalization. You're worried about the velocity of the most of this mass and most of this energy is coming from much later, from line observed directly at late times. So most of the energy is not carried by the high velocity material.
Okay, I'm saying if you get this wrong, I will have no confidence in the other part.
Okay.
That's the way I'm worried.
Okay, maybe. It's
Okay, it looks like, another question, please.
Yeah, if you say the I guess the short GRBs, you can see it only within 200 megaparsec.
the neutron star mergers we can see within 200 megaparsecs. Yeah.
Okay. How often are we supposed to see it?
We don't know because we don't know what is the true rate. The expectation is that LIGO, when it will be in full capabilities, we'll see hopefully more than one, possibly dozens. Really, hopefully more than one. Well, by now they already saw black holes. They did what they need to do, but
0.4 to 400.
yeah, this is a canonical number that they give.
Over the lifetime of...
No, a year.